Saxon Advanced Algebra Lesson 65. Sorry, we were in the middle of this first example. We were resolving the radicals and the trig equations, and I was saying that we have to check our answers for spurious roots, right? Answers that were created when we squared things up that don't necessarily work in the original equation, and that we're not checking so much the angles as we're checking these roots, right? This is what we're checking, is to see basically what is normally the question is, do both positive and negative really work in the original equation, or did we just kind of paper over that difference when we squared things up? So we don't have to check all four angles. We have to check one angle from the positive side of this and one angle from the negative side. So let's do that. I'm going to copy this down here. We said that the sine of x equaled plus or minus square root of 2 over 2. And then we said our values for x were 45, 135, 215, 225. 225 and 315. Okay, those are the angles that yield a sign of positive or negative. But we have to check and make sure that this works in our original equation. So first let me write the caution. And besides, I just want another opportunity to say spurious roots because I think that's really fun. Okay, so this is my cautionary warning to you. The easiest way to do that is to change this into a decimal number. You can use your calculator to do that. Square root of 2 divided by 2, and it equals 0. .707. And depending on what quarter it is, it may be positive or negative, right? So we'll have to check that. So let's try the original equation. We don't have that on this page, so let me write that again. It's sine of x minus 1 minus a sine. Okay, I'm just copying the original equation. And then we're going to test that for, let's test the second group. I'll tell you right now the first group work. I want to show you what happens when it doesn't work. So we're going to use the 225-degree angle. So we'll say the sine of 225 minus and remember that's squared. You have to, it's kind of a trick to get it all right. In the third quadrant, which is where 225 lives, right? Here's our 225-degree angle in our third quadrant. And we see that sine is negative in that quadrant, right? Sine is the second of the two numbers. I think I mentioned this before the connection broke, that what was I going to say? Oh, if you haven't watched how to build a unit circle and how to use it, please do. It's a half hour of your time that will change your life and makes these calculations so much easier. If you haven't watched that yet and don't know how to build a unit circle, you probably are looking at this thinking I'm insane, but it will change your life and make math so much easier. So please watch it. Search me. Search my YouTube channel, Unit Circle, Saxon Advanced Mathematics Unit Circle is the name of the video. And like I said, it's half an hour. You download this PDF or you just go grab a plate out of your kitchen and trace a circle. You can do it like that too. Okay, so we want negative 0.707 to be our value. We're going to substitute that in. Okay, so we're going to say negative 0.707 minus the square root of this whole thing, okay? And again, don't do this by hand. Once you get this plugged in, again, use the decimal numbers rather than the radicals. It makes it easier to run through your calculator. But go ahead and push this through, and what you will find is that this is false. So what that tells us is that the angles associated with negative square root of 2 over 2 are spurious. So that means, going back to our original list, I'm going to write them all down again just so you can see them. We said 45, we said 135. If you test this for those, you'll see it's positive. 225, we just found out doesn't work. And 315 is the other angle that's associated with the negatives, right? These guys don't work. So our answer is just this. Okay? And on a test or a review problem, this is exactly the way I would want you to show it to me. Show me the ones crossed off that don't work and keep the ones that do. Yay, that's the right answer. Okay, and we have one more of these. So let's try the next example. It is 65.2. And it says solve these are starting to look really hard, aren't they? I mean, and they are. Okay, so that's our trig equation that we're supposed to solve. And John tells us, check this out. This tells us that John wants his answer not in degrees. He wants his answer in rads. Whoa. Whoa, whoa, whoa. Okay, so what we're going to do is we're just going to work it in degrees, and then at the end we'll convert it to rads. As you go forward with your math problems, you will eventually, the speed is personal, you'll eventually become more and more accustomed to rads, and you'll probably get to a point, if not in this course, then in the next course you take that has trigonometry, you'll get comfortable enough that you can work problems in rads, especially if you're using the unit circle, because we've got the rads and the degrees right next to each other. So it's pretty easy to just grab the other set of data. But if degrees make you crazy, I mean, no, well, maybe degrees make you crazy too, but if rads make you crazy, that's fine. Don't use them. Just work in degrees and make sure you understand what the heck you're doing, and then you can deal with radians. I am going to work it in degrees because I don't want to confuse anyone by jumping straight into radians. I want you to make that transition in your own pace. But if you're comfortable now working in radians, feel free to do so. Okay, what this tells us is not that we necessarily have to multiply these together. What this tells us is our old friend, the zero product theorem, that if we're multiplying two things together and it equals 0, then either the first thing equals 0 or the second thing equals 0. Oh. That was a really nice way to go from something that looks really impossibly hard to something that looks much more manageable, doesn't it? So now what we're going to do is we're going to solve each of these and find angles that would make each of them true. So this one says the tangent of x equals positive square root of 3. And this is tricky because tangent is not our unit circle. So we have to remember that this means sine over cosine equals the square root of 3 over 1. So now let's look at angles. And we know, okay, this is probably going to be the pattern where there's two other numbers and they cancel each other out, but we want sine to start with a square root of 3 and cosine to start with a 1. Sine to start with a square root of 3 and cosine to start with a 1. Okay, so that would be like this angle. And it would be the opposite angle because we want it to be, we want tangent to be positive. So this would give us a positive tangent, and this would give us a positive tangent because they're both negative, right? Two positives, two negatives. These two will not work because they have one negative each. So that means our tangent would be negative, but our tangent is clearly positive. So it's, we can use the angles where x equals 60 degrees and x equals 240 degrees. All right. And just to test these, remember that at 60 degrees, for example, sine is square root of 3 over 2 and cosine is 1 over 2. So we have a complex fraction, but if we multiply by the reciprocal to turn this into a 1, that goes away and that cancels, and there's where we get the square root of 3 over 1. If you can do those simplifications in your head, do it. If you need to write them out, do it. But whenever we're looking for tangent, we look at what the answer needs to be, and then we look at our unit circle to play around to try to find an angle where the sine and cosine will give us the tangent that we want. We don't have tangent on here, so we have to play around with sine and cosine in our head to make it work. Okay, so according to this, the angles of 60 degrees and 240 degrees will make this come true because it'll make this turn into a 0. Now let's see if there's anything that will make that turn into a 0. So we'll do the same thing. We'll correct, or not correct, but we'll play with the algebra. Get that over there. Now we're looking for angles where sine is equal to -1. That sounds quadrantal to me, doesn't it? Sine is 0, 1, 0. Oh, here it is. Let me turn it so you can see it. Sine is the second number. Sine is -1 at 270 degrees. So that sounds good. But we know that tangent in some of the quadrantal angles, right? Sometimes tangent is undefined when we're at those quadrantal angles. So we better check that just to make sure that 270 isn't one of the angles where it's undefined. If you've memorized it, great, you probably already know the answer, but you don't have to memorize it, we can figure it out. So the problem is 270 works great in this part, but if we try to find the tangent of, if we put 270 in for x, it's going to be in both of these places. So we have to make sure that we're not going to freak out the tangent on this side. So the tangent of 270 degrees equals sine over cosine, as it always does, right? So then let's look. Sine is -1, cosine is 0. Shoot. So Kingdom is trying to blow up right now. So tangent of 270 degrees is not going to work. Again, we didn't calculate 270 on the tangent side. We calculated it over here as a possible value in this binomial. But if we plug 270 in here, we have to plug it in here as well, and that's where everything went crazy because tangent of 270 is undefined. So this is not an acceptable answer. And the final solution, ooh, I don't like that expression. the final answer is composed of just those two angles. Does that make sense? This is the problem. Last time we had spurious roots because of the fact that we were squaring up radicals to get rid of them. This time we have, it's not really a spurious root, it's an undefined value that we had to eliminate, right? So this is another one. These are tricky problems. These are very difficult problems, and if you are understanding them at all, you're doing great. All right, next we're going to talk about, and we're just going to do one problem. Graphs of log functions. We've already talked about this a little bit. And remember that a function is simply a mapping. Anything that we can graph on the Cartesian coordinate system is technically a function because it has an x and a y. It has two variables that we map in relationship to each other. Now, we've graphed exponential functions. I need to make it go this way too. And we know that they do this thing, right? This is the point that's magical. This point is 0, 1. This is a graph of a function where the base is 1 or greater. And then we also know that we can graph log functions, and they go like this, right? And they have their magical turning spot, unless the base is super weird, at 1, 0. Now, okay, let me just write down the equations that these are. We're just using a base of 2 for these, right? Now, what I want to talk about is what happens if we put these equations on the same quadrant. So I'm going to draw that here. This one goes like that. This one goes like that. And I'm just eyeballing these. This is the exponential function. This is the log function. What happens, if you do it perfectly, and we're going to do it more perfectly in a minute. They form a symmetrical pattern around the line that goes through the axis. What? They're mirror images of each other on the line y equals x. That's that red line. Okay? That's really helpful because what most people find is that graphing the exponential function is far more comfortable. Graphing a log function feels kind of creepy and weird. But if you do the exponential first and then draw this line in, it will make it much easier to make sure that your log function is correct. So for our last problem, we're going to graph the exponential and the log function and see if they give us that nice patterny pattern. Okay, the thing I want to remind you too before we start graphing is that this is the form of the exponential function, and this is the form of the log function. And I'm just using base of 2, but it can be any base as long as they match. Remember that function just means a mapping. It just means drawing a picture of the relationship between the x and the y, or the n and the l, or whatever it is you're choosing. And that's what these are. These are exponential functions and log functions. The word sounds like it's something more than it is. It's just the picture of what happens when you graph all the different pairs. Okay, so what we're doing, remember, when we graph these, is we're graphing the same two variables. In the exponential function, we'll pick our L's and then we'll calculate our N's. Then we'll use these same N's over here to calculate our L's. So we're gonna get opposite pairs of each other. Opposite? You'll see. Example 65.3. This is the log function we're being asked to graph. Y equals and it looks like it's going to be really hard. Okay, log equals 3.5x. 3.5? What in the world? But don't worry, it's easy. Remember that this is the number. On our graph, we're going to call it n. This is the exponent. And on our graph, we're going to call it L. All right? That's the way log functions are always written. We're used to seeing this over here, but this is the number, and this is the exponent that you put on the base, right, in order to get that number. So what we want to do first is we want to rewrite as an exponential function. Okay, an exponential function looks like that. So it will be x, because x represents the number, equals the base, 3.5, raised to the y power. Okay, and then I remember that this represents, I'm going to write it again with the n's and the l's. Right? So I've taken this and I've rewritten it as an exponential function. Now I'm going to make my graph of values. Now there's a couple values that I really like. This is my exponent and this is the number that I'm going to get. 3.5 to the L. I want to choose 0 because 3.5 to the 0, oh gosh, it's always 1. And I want to choose 1 because that's also really easy. Anything raised to the first power is itself again. So even though our base is disgusting, by choosing these really simple basic values, I will be able to graph this really easily. So now I'm going to draw the full 4-quadrant graph because I know I'm going to be putting both the exponential function and the log function on here. So let's see what I've got. 0 and 1, oh gosh, just like I always want. And 1 and 3.5. 1, 2, 3 and a half. So my second point will go there. And then I know this is going to trail off. Okay, so this is my exponential function. N equals 3.5L. Now, I also know that when I go to graph the log function, I'm going to be using these same values for n, and I'm going to be calculating these values for 0. If the exponent, if the number I want is 1, then the exponent I put up here is a 0. Wait, I need to write it as a log function. I was putting that in the other one. Okay, we don't really have to rewrite it as a log function because it's what we were given. So now we're saying, we're going to put in the L and the N. L equals log 3.5N. Okay, so now we're choosing the numbers we want and we're figuring out what log we would put on them. And I'm going to use a separate piece of paper to show you that calculation so that we don't have to turn to a new page. Okay, I'm going to write it again up here. L equals log 3.5 N. I'm just copying this. That's the original problem. And what we want to do is we're going to be choosing our N's and calculating our L's. Notice it's the exact, oh wait, no, don't look at that. Notice that our graph, our chart for calculating the values is going in the exact opposite order, right? This was L to N, this is N to L. So I'm going to choose these same N values, and let's calculate them using our log function here. If the number that we want to get, this is the calculation I'm making, which is the very same as right there. If N is 1, that means that's the number we want to get. What's the exponent we put on 3.5 if we want to get a 1? Well, 0. Okay, now our number is 3.5. What's the exponent we put on 3.5 if we want to get 3.5? That's 1. So we calculated them independently, but look what happens when we compare. 1 is associated with 0. 3.5 is associated with 1. It's the very same chart, only backwards. So now we're going to graph these points. And I want to point out that you really don't have to make two charts. You make the first chart, graph it the normal way, then just graph it backwards, and that will give you the log function. So our first point is 1, 0, and it's right there. Our second point is 3.5 and 1. So 1, 2, 3.5, there's 3.5, and 1. So this is our log function. And I'm going to write L equals log 3.5. And I like to write the equation right close to them. And we can see, even better than last time, that this line function of y equals x splits right down the middle and creates mirror images. So, I don't know about you, but I feel better about exponential and log functions when I see them on the same graph. Seeing them separately is fine, but they make a lot more sense to me when they're on the very same graph, and when I can compare the calculation of the points to one another, I see they're just mirror images, and that's why their graphs are mirror images. And that's because their equations are mirror images, or we can call them their functions are mirror images. So exponential and log set each other off really nicely, and again, most students find the exponential easier to grasp and easier to graph. And so if you get one in and then imagine that line, it makes it a lot easier to make sure you're correct on the other one. All right, I will really want to make sure this sets into your brain. We're not going to go a lot farther with it, but this is something that most college classes pick up on and spend more time talking about. And I want you to go into that feeling really comfortable that exponential and log functions are just, it's like having, okay, here's a metaphor, ready? It's like having two pairs of socks, but one of them is turned inside out. They're the same thing. They look a little different, but with just a little bit of work, you can turn them back into two inside out socks or two right side out socks, whichever you prefer. So exponential and log functions are not scary. They're just socks. There, that's my thought for the day. Okay, that's the end of lesson 65. Thank you, goodbye.